So let us now discuss enhancements to the directory protocol. So the directory protocol, as was described in the previous lecture, is correct, is complete, but it is not efficient. So let us first list some of the common problems associated with directories and how we will fix them. So the first is that we need an entry for each block in a program's working set. So recall that the working set is defined as the amount of memory that the program uses in a short period of time. So of course there is some subjectivity in this definition, but there is a somewhat better definition in the book that talks about the short period of time in terms of the phases that a program goes through. So a program typically has a settled phase of execution, then another settled phase of execution. So in these settled phases, roughly it uses a constant amount of memory and it works on that. So that's the working set. So for each block over here, we need an entry in the directory, right? And so this is required, and this is required for all the cores. So the directory per se has to be huge. In each directory, we need an entry for each constituent cache, and that adds to the storage overheads. And given the fact that we have a single directory, that itself can become a point of contention. Hence, we have to look at solutions to make this simple idea an efficient idea. So what we can do is that we can take care of the size and contention problems like this, that we take the physical address space and we partition the physical address space into different disjoint sets. So this is set 1, set 2 and so on. So we just partition the physical address space. So one nice way of partitioning is, instead of partitioning by the MSPs, we partition them by the LSPs of the block address. It will be far more uniform that way. And for each partition, we assign a directory. So we can have multiple directories. That is not an issue. And given the fact that a single block will always be mapped to a directory, to the same directory, correctness is not an issue. So what we do is that we split the address space and each partition gets mapped to a directory. A directory will then handle all the requests for the part of the address space that it owns. So this also resolves the issue of the single point of contention, in the sense that we have multiple directories that look at different addresses. So based on the address, a message can be routed to the correct directory on the NOC, and that directory will have a smaller size as compared to a large big combined one. So now let us come to the list of sharers. So how do we maintain the list of sharers? So one is a fully mapped scheme. So if there are n processors, and assume I have one sister cache per processor, I can have a bit vector of these n sharers, right? Capital N sharers, where each block is associated with a bit vector of sharers. So if I have 64 sharers, I need to have 64 bits or 8 bytes per block. So I can have a slightly more space efficient solution. What I can do is that I can have a single bit for a set of caches. So instead of 64, I can break it into maybe sets of 4 and have 16 such sets. So this could be set 1, this could be 1, 2, 3, 4, right? First 4 bytes. This could be set 2, set 3, set 4, and so on and so forth. And so then if I have a 1 over here for a set, it will indicate that at least one of the sister caches within the set has a copy of the block, right? Then what we can do is we can run a small Snoopy protocol inside the set, or we can essentially query each of the caches within the set by sending a multicast message. Something of this nature is possible. And so there are two advantages. One is that this reduces the storage space at the directory, that is point 1. And the second is that this is naturally amenable to the structure of a modern multi-core system, because a modern multi-core system is typically broken down into tiles, where we have like these caches and cache banks, cores and cache bank combines, right? So where we have a single tile will have a core and a cache bank. So in a certain sense, within a tile, they share a bus. So nothing stops us from having a like a local Snoopy protocol running here and an overall directory protocol. So that will ensure that in each set we have an order of writes and we also have a global order of writes. The other is that we store the IDs of only k sharers. So this is like a partially mapped scheme that only for k sharers, we store the ID. So we just say that look, we will only store the IDs of k sharers. That is because typically most blocks are not associated with that many sharers, right? So maybe we'll have like 2, 4, 6 maximum sharers. So let's say if we do for 4, and so assume we have 64 blocks and we store only for 4 sharers. So what we need is we need 4 into 6 bits, which is 24 bits. And after that, we can have an overflow bit that stores the fact that there are more than k sharers. So the overflow bit, which will be one additional bit over 24, will be 25. This will essentially indicate that look, we have more than k sharers. But the overflow bit will, the fact that it is being set will indicate this, but this will be a very rare event. In the sense, we expect very few blocks to have more than k sharers. So in this case, we can revert to a mechanism where every message is broadcasted to all the sister caches. And this of course will be much slower, far slower, but given the rarity of this event, this is perfectly doable and is done also. It is known as the partially mapped scheme, which is reasonably popular. Now let's come to the size of the directory. So the directory should ideally be as large as the number of blocks in the program's working sets. You might not have one program, you might have many programs. So the directory should ideally be as large as the sum of the working sets. Since you have multiple directories, of course, the blocks will get partitioned, but at least the directory as a whole should contain all the blocks. So, of course, having an entry for every block in the physical address is impractical. So, the way a directory is designed is that it is designed as a cache, similar to a set associative cache, right? With the same thing that we use certain bits of the block to address the offset and index and all of that. So, it is designed the same way as a set associative cache. And it does keep the state of a limited number of blocks because after all it's a finite sized cache, and it's organized, so it's organized exactly the same way as a set associative cache with a tag array and the data array. And the tag array in this case is some bits on the block address, and the data array in this case will contain the list of sharers and the state. If an entry is evicted from the directory, what do we do? Well, what we do, so this is why the size of the directory is important. So if it is a shared block, so furthermore we can say that look, certain parts of the address space are either read-only or private, so they need not enter the directory in the first place itself. But if let's say it's a shared block, then it has to enter the directory, and if it is evicted, we need to invalidate it in all the caches. This is the overhead, this is the problem, and this is why we need large directories in the first place. That we don't need it, and this is exactly why we did all of those optimizations such that we can store as many blocks as needed in the directories, right? Because evicting a block from the directory is expensive in the sense that all the caches that need it, they also need to discard it. A few more issues. So we can have a new kind of a mess in a multiprocessor system which we didn't have in a uniprocessor system. Consider a 64-byte block. It is possible that different threads access different memory words within the block. So consider a block like this, which is let's say 64 bytes. Possible that thread 1 accesses these set of bytes and thread 2 accesses these set of bytes. If they are accessing these bytes concurrently, what will happen is that one thread will invalidate the block, then the other thread will invalidate the block. So the block will just keep bouncing between the threads. But in effect, so this bouncing will reduce the performance, But there is no true sharing in the sense the same set of bytes are not being shared. This is false sharing. Why is it false sharing? Because we are accessing different sets of bytes and these bytes are disjoint. They are not the same, but they happen to be located in the same 64 byte block, which is causing the block to bounce, because blocks for us are atomic units. So to reduce such fault sharing misses, we need to use a smart compiler that places data far more intelligently and smartly. And the smart compiler essentially, with an intelligent placement of data, can reduce the amount of fault sharing. Also, when we design a real cache coherence protocol, as we saw in the Moesi protocol, so in the Moesi protocol, actually, we didn't have 5 states. If we include the temporary states, we had actually 7 states. So there are a lot of interactions in real hardware, and lot of events can happen. So it's possible that multiple messages or different types for the same block might arrive at the same time. Along with that, we might have context switches, we might have interrupts, we can have a lot of things, right? So to capture all of these interactions and to have a state diagram that captures all these combinations of events, right, which will be concurrent events, we need to do a lot. So whenever we have such concurrent events, so let us say one event could be that I want to transition from the M to S state, and at the same point of time another uh, so I receive a read miss and a write miss at the same time. So do I transition to the S state or do I transition to the invalid state, and who sends the data to whom? So all of these concurrent events, right, to the same set of to the same block, which can cause problems, these are known as race conditions, and all such race conditions need to be handled, because we don't want a single corner case to kind of derail the entire cache coherence protocol. Hence, if we consider all of these things and we design a practical cache coherence protocol, we can very well have 100 plus states. So it is not unknown and it's not uncommon or unnatural to have 200 plus states in a cache coherence protocol. And of course, it is not possible to verify that the protocol is correct, but we can have an automated verifier which can take the state diagram and verify if the protocol is indeed correct, in the sense that whether it captures all the corner cases or not. Alright, so now we will extend the basic cache coherence protocol to implement something which is very important called a critical section, and implement atomic operations which are also synchronization operations. So this is a quintessential example that is given, that where we want to update the balance of a bank account. So in this case, we just want to add, I'm using the Indian rupees over here. So we want to add 100 rupees to a bank account, right? So, in international viewers replace rupees with dollars or your local currency, it doesn't matter. So rupee is the Indian national currency. It is also said as INR, Indian National Rupee, and this is the symbol. So we add 2 lines like this. So let's say I want to add 100 rupees to my bank account. So what we do is we read the balance in the account, which is a load operation, put it in a register T1. We add 100 to it, and then we put the register T2 again back with a store operation. We want all of these to happen atomically, in the sense either all 3 happen or none happens. So unfortunately, this code cannot be executed in parallel by multiple threads, in the sense that multiple threads try to update the bank balance, the same account balance at the same time. The execution can sadly be incorrect. Let us see why. So let us look at this, right? So I'm already putting an incorrect symbol over here to draw your attention to the fact that, look, a mistake is going to happen. So let's assume that the original balance was 100, and then I add 100 more, it becomes 200, and then the final balance is 200. So then here each line corresponds to a line of assembly code, as you can see, a load, a register add, and then a store. So let us assume that we have two threads running the same piece of code and the two corresponding lines execute in parallel. A lot of problems can happen. So the final answer will be wrong. The final answer should be 300 because we are adding 100 twice, but we will see that that will not happen. So what will happen, let me erase the ink over here and you will clearly see what is my problem. The problem is that if both these lines execute roughly at the same time, both will read the original account balance to be 100. Both will then locally add 100 to 100 and make it 200. And finally, both will store 200. So the point is that if this happens, the final answer will be wrong. The final answer should be 300 because we are adding 100 plus 100 plus 100. But what we see over here is that because there was no synchronization between these two pieces of code, the final answer is 200, and that is not correct. And the reason basically is that we have a race, what is called a race condition, that the same address, we are simply reading both the threads are reading it to 100, they are computing the new balance and writing it back, and the final answer is not correct, it's wrong. And what would have avoided this? Well, what would have avoided this is if this entire code block would have executed before this entire code block or vice versa. So in this case, the starting balance would have been 200. We would have set this to 300 and finally written 300. So one solution is that we restrict this piece of code. So we say that before we enter it, we somehow lock it. We will see how. And this ensures that two threads cannot be executing this piece of code at the same time, only one thread can. And then once it is done executing, we unlock it. So this ensures that only one thread can execute this piece of code, then another thread, then another thread. So this is set to execute atomically. Right, what does atomically mean in this case? It means that either all three lines appear to execute instantaneously, is the same as the definition of atomicity in the case of a write, that either all three lines appear to execute instantaneously or they appear to execute not at all, or it appears that they have not executed at all. So in this case, if these three lines execute atomically, then we will find that first the balance will be updated from 100 to 200 and then from 200 to 300. The way that this is done is that we create a critical section. So this piece of code with a lock and unlock is a critical section, also known as a CS. In the critical section, this lock function returns when the thread has exclusive access to this piece of code. No other thread can simultaneously execute. And unlock kind of relinquishes the lock. So how do we use atomic instructions to implement locks that are a vital aspect of the critical section? For implementing lock and unlock functions, we need atomic instructions. We'll see in a second what they are. So an atomic instruction is similar to an atomic critical section in the sense it either executes completely or not at all. Nobody observes a partial state. In addition, most atomic operations also act as a fence. And so that fence property is there, which basically says that all instructions before it complete, then the fence executes, and then all instructions begin. So let us look at one atomic exchange operation, which we will also call the synchronizing operation. In a second, we will see how that works. And an atomic exchange operation will look like this, right? And we will use the coherence protocol to implement it. So we will see how. But the way that it looks like is it takes two arguments, a register and a memory. Instantaneously, or let's say it appears to execute instantaneously, it atomically exchanges their contents. So register's contents go to the memory's contents go to the register. So this is an atomic exchange instruction, and almost, well, not almost, all instruction sets that are commercially used have such atomic instructions because they are required. Without them, we will not be able to implement locks. So in x86 instruction set, if we just add the lock prefix to an otherwise non-atomic exchange, it becomes an atomic exchange. And an atomic instruction is expensive. Well, why is it expensive? Well, number one, it does a write in the sense, you're reading it and then you're writing it. So in that sense, but that's not that expensive. It's more expensive because it's a fence. So a fence essentially prohibits out of order execution between instructions on both sides of the fence. This is why these instructions are very expensive, but they will be used to implement what we call synchronization edges in our execution witness. We will see in a second how. So let us again look at an atomic exchange. So an atomic exchange, what it does is that it exchanges the contents of a register and memory, and that too atomically. So nobody sees a partial state in the sense that, let's say this contains 3, this contains 5. So you will either see 3, 5 or you will see 5, 3, but no other state. Let us now look at the implementation of a lock function in assembly. So the lock function uses an atomic exchange instruction as is visible here. And so we assume that XCHG in this case refers to atomic exchange. So what we do is that every lock function needs to have an associated lock address. So let us assume that the register R0 contains the lock address, and furthermore the exchange instruction also contains a fence. All right, so the exchange instruction is a synchronizing instruction. So along with doing an atomic exchange, it contains a fence as well. And furthermore, the semantics of the lock is such that if the memory address contains 0, it means that the lock is free, it is not acquired. And if the memory address contains 1, it means the lock has been acquired by some thread. Right? We don't know which thread, but some thread has acquired the lock. So now the way to acquire the lock is these two pieces of code. So we move 1 to register R1, and then we exchange the contents of R1 with the lock address. So at the end of this atomic operation, the lock address contains 1 basically, but that's not important. So this anyway we are doing, but what we care about is the value of R1 because that will contain the old value of the lock address. So the value of R1 is 0. This means that this instruction essentially acquired the lock, so it set the status from 0, it set it to 1, which means that the lock was free and now it set it to acquired. So this means that the current thread has acquired the lock. So we compare R1 with 0 if it is not equal, which means if R1 is 1, this means that the lock was acquired by some other thread prior to this exchange instruction. Hence we have not acquired the lock, so we go over here. But if R1 is equal to 0, it means that the previous value was 0. And of course the current value is 1, so we have acquired the lock, so the function just returns. So pretty much it keeps on trying to acquire a lock in a loop over and over and over again until it gets the lock. Alright. And the unlock function, what we do is we do the same thing. We store 0 at the lock address. So again we use an atomic instruction for this purpose. And the reasons will be clear very soon. So we put 0 in R1 and then we do an atomic exchange. So in this case what we do is that the contents of 0R0 come to R1, but that's not important. What is important is the contents of R1 go here and the contents are 0. This means the lock is free. And after that we return. And given the fact that this instruction, so there is no need to loop, and the reason there is no need to loop is because this instruction will be successful at some point in time, right? So that is essentially a requirement of coherence. So we'll see how it extends to such atomic instructions. But pretty much the idea is that we just need to execute it once. We need to set this to 0 and move out. In both cases, we are using this atomic instruction, which also contains a fence. Alright. So this is the lock function and this is the unlock function. So the unlock function does not have a loop, but in principle, the lock function might keep on looping till infinity because it will never get the lock because another thread is taking the lock. So implementation of atomic exchange. So how do we implement atomic exchange? All right. So what we do is that, so the general format is you have a register and a memory address. So R1 needs to be put into some temporary storage location. We will read the value of R2, right? So R2 is a memory address. So the value of the address, whose the value stored at address R2, that will be put into R1, and then the final is the last step is that we'll do a store operation, put temp over there. So this is essentially what is called a read, modify, write operation, in the sense that we are reading this memory location, there is a read, and clearly we are modifying. So in this case, we are not modifying, R1 is still being kept, but maybe we can have an increment operation also where we change it. So that would be a modify, and then we have a write. So it involves three steps: a memory read, a memory write, and a register move. All three of them need to appear to happen instantaneously or need to happen atomically. And such kind of a read, modify, write instruction that combines a read, some sort of a register movement, right? And then a write is what we want to implement using an extension of our cache coherence protocol. That is the challenge that lies in front of us. All right. So the method for this is like this, that we get exclusive access with write permissions for the memory address in R2, right? So that's the first thing, that we get exclusive access for this address, right? So this is the exclusive access that we get. The way we get it is that we essentially get the line in the M state, right? So basically the line is set to the M state. So we have write permissions for the memory address in R2. So this can be gotten by getting a write miss on the, by placing a write miss on the bus. So we get exclusive access. Then we perform the operation, in the sense we read the register and then we read the memory location into the register. And finally we transfer the old value of the register into the memory address. All right. So we perform a swap. So the interesting thing is that the way we guarantee atomicity. So the way that we guarantee atomicity is that after getting exclusive access, we perform these three operations quickly. All right. So the question is how. So first is that in an exchange operation, we need to understand that there is a fence, right? There is a fence within it. So we wait for the exchange operation to reach the head of the ROV, right? So we just wait for the exchange operation to reach the top. And so this will guarantee that all the instructions before it have completed and gone away. And after that, it is possible that some writes might have been delivered to the memory system, but they would not have reached their final location. So at this point, we would flush the write buffers and MSHRs and so on, and pretty much get an acknowledgement from the memory system that all the instructions which were fetched before the atomic exchange have all completed totally, and no other instruction after the fence will be allowed to perform any read or write. So we'll pretty much stall that part of the execution. So that is the fence part. And after this, once exchange reaches the head of the ROB, that is when this is sent to the memory system. So the memory system, the first thing that it does is it gets exclusive access, and till the time that the exchange operation is not completed, so interrupts are not delivered. And I mean, think of it that way, that interrupts are kind of kept on hold, and interrupts will only be delivered to the next instruction, not to this. And there are variants of this instruction that additionally provides a status of whether this could execute successfully or not. In that case, interrupts are delivered, so this instruction can be executed partially. So then of course the user will know that this instruction didn't execute successfully. But let's for the time being assume that this executed successfully. So what we do is we get access to the line in the M state. We quickly perform the swap and then we perform the write, and we wait for the write to fully complete, which means that we need to flush off the write buffers and MSHRs and all intermediate buffers. So pretty much the architecture has to provide some kind of a mechanism to ensure that a write has fully completed, right? So some sort of a mechanism for complete completion of writes needs to be there. Most of the time, just flushing the buffers is good enough because the writes ultimately then head towards their final destination, right? So while this instruction is being done, it is possible that we might get other requests from the local cache or other caches or the directory when the operation is in progress. So it's possible we have read but we have not written, and then suddenly a write miss comes. So the question is, what do we do? Well, we do not respond to any of these requests until the atomic exchange is complete, and only when the operation is over do we respond to the directory or other caches, right? So for us, executing an atomic instruction is kind of heavy. The overheads are large in terms of performance, and the reason that the overheads are large is like this: because we have a fence, that's number one, and number two, when we need to also execute this instruction very carefully, in the sense that after we start, we simply do not respond to any message, and we quickly perform the memory read write register move, and then we respond to other messages. So this ensures that this instruction cannot be interrupted in the middle. All right. So now the question is that if you haven't understood up till now, why did we design the lock in this manner and why do we need a fence? Well, so the idea basically was that we will have a piece of code, a lock. So we'll keep on spinning on the lock address. That's why it's also called a spin lock. This process has a lot of overheads in addition to the fence. So we will see what. But pretty much the idea is that the reason it acts like a fence is because none of the instructions in the critical section should actually execute before the lock, right? Because if they actually do, then the notion of having a lock that kind of breaks down. So that is the reason we need to have a fence here, that we acquire the lock first and then the instructions in the critical section execute. They completely finish, and after that an unlock operation happens. That's the reason we need one fence in the lock part and one fence in the unlock part. All right. So now if we also think about this piece of code, I want to raise one more point before I actually move ahead. So if we actually look at the structure of a critical section, here is what you're going to observe. What you'll observe is it starts with a lock, then we have the code and then an unlock, again a lock and then an unlock, and so on. So the key instruction over here is the atomic exchange instruction. So if I just look at the program snippet of all of these atomic exchange instructions across all the threads, I claim it will be in SC. Well, why? Because SC is program order plus atomicity. Program order is clearly being maintained because there is a fence within these instructions. So program order is clearly being maintained. And given that these are atomic instructions, atomicity is also being maintained. So the synchronizing instructions, the synchronization instructions, in this case these are all the exchange instructions. If I were to just consider them, then they will be in SC, and this is an important property which we will use later. So bear this in mind, keep this in mind. Alright, so now coming to the lock process, what we do is we do an atomic exchange. We see if we set the lock from 0 to 1. If not, we try again. If not, we try again. So we keep trying. So in each try, what we are essentially doing is that we are locking it in the M state and we are trying to perform the swap. And if let's say there are multiple threads that are trying, all of them are locking it in the M state. So the block will pretty much bounce between these threads. This will add to the overheads quite substantially. So that's the reason there is a more efficient version of this lock, So it still uses a fence, it still uses an atomic exchange. So it does all of that, but it is just that the number of these line bouncings is much lower. And let's see how that is constructed. So in this case, what we do is that this is a lock function. So we move 1 to R1. So we first test if the lock is free. So what we do is that we load the value of the lock into register R2. We compare it with 0. And then if it is not equal to 0, then we again come back. So we again, so here also we run a spin loop, right? Here also we run a loop. It's called a spin loop. But instead of having the costly, expensive exchange instruction, we have the simple load instruction. So what will happen is that if, let's say, one thread holds a lock and the rest n threads are trying to acquire it, all of them will ultimately have the line in the S state, and they can only be spinning on their local copies, and this is going to be a very fast instruction, right? This instruction is going to be extremely fast because we have replaced an expensive exchange instruction with a less expensive load instruction, where the cache line does not have to be locked in the modified state. So here, since we'll be operating only in the shared state, all that a thread needs to do is it needs to spin on its local copy. Once it finds its local copy to actually be 0, well, then it will attempt an exchange only when it thinks that the lock is free, when it reaches 0. In that case, what it will do is it will exchange R1 with the value of the lock. It will compare R1 with 0. If it is equal, it means we have gotten the lock. That's great. Otherwise, if it is not equal, it will again jump back to test. And again, we will keep on spinning, but we'll in the spin, we will not do atomic exchanges. We'll just do a read. And when we see some hope, when we see the lock to be free, we'll again try to attempt it. So there are power efficient versions of this, in the sense we can add a random delay, or we can add what is called exponential backoff. That initially we wait for some time, which is, let's say, t units, or a maximum of t units between 0 and t units. Then another, if let's say we are not successful, we again wait for some time which is between 0 and 2t units. Again we wait for random duration which is between 0 and 4t units, and so on. So ultimately this works, and with extremely high probability we actually acquire the lock. And given the fact that we acquire the lock, well, what's left? Then we return and we execute the critical section. Unlocking is simple. So this is the same as the basic exchange lock. So we will call this the tax lock, the test and exchange lock, as compared to the basic version. So in this case, we just exchange the contents of R1, and since R1 contains 0, 0 goes over here, so the lock becomes de facto free, and then we return. All right. So this is the basic structure of an optimized version of the lock acquire algorithm, where instead of the exchange function, we use the test and exchange function, where the spin loop is on testing, and in the spin loop we have a much cheaper load instruction as opposed to the expensive exchange instruction which had a fence. Right, it had a fence, it had a write, it had all of that stuff. But in this case, because we have a load, it is possible for multiple caches to have the block in the shared state. So we only spin on the local copy or in the local cache. So it turns out that there are a large number of additional atomic operations, not just an atomic exchange. So one of the most common ones is a test and set. So here, let's say we have tasks R1, 8R0. Let 8R0 be the address of the lock. I've kind of generalized it. So this is the pseudo code of it, and the entire pseudo code executes atomically. So here, if the lock address is equal to 0, we set it to 1. We set the value of R1 to 1, which indicates success. Else we set the value of R1 to 0, which indicates failure. Then we have fetch and increment. So in fetch and increment, what we do is we again take a register and a memory address. The contents of the memory address are transferred to the register, and we increment the contents of the memory address So 8R0 is equal to R1 plus 1, which is previous value plus 1, and this happens atomically. So we can extend this to fetch and add, where you have two registers in the memory address, assuming the ISA supports it. So in this case, we read the old value of the memory address, and the new value of the memory address is R1, which is the old value, plus an offset R2. Now we will discuss two more synchronization operations which are regarded as extremely powerful. What makes a synchronization operation powerful? I'll discuss that a few slides later. So the first one is compare and set. So in compare and set, we compare the memory address 8R0 with the value of a register R3. If it is equal, we set the value of 8R0 to R2, and we set R1, which is the flag saying success. Otherwise, if you are not able to do this, we set R1 equal to 0, which indicates failure. Alright. So what do we do? What we do is that we read the memory address and we compare it with the value. If it matches, then we set it to the value of this register, and we set R1 to 1, indicating success. Otherwise, we set R1 to 0, which indicates failure. Then let's look at another pair of synchronization instructions. This is a pair, okay? So unlike the other ones, it's a pair. It's always meant to be used in pairs. It's called load linked and store conditional. So the first load linked looks like a regular load, but it's just a synchronizing load. So R1 is equal to 8R0 means the contents of the address are sent to register R1, right? And so basically, so if you actually look at the cache instruction, I'll tell you a quick difference. If you haven't seen it up till now, the cache instruction actually requires 4 arguments, 3 registers and 1 memory. Most ISAs will not be able to support it unless we do a little bit of trickery here and there. But the LL and SC pair is nicely supportable by most RISC instruction sets. So if you see the first instruction, it's a regular load, but it's slightly special in the sense it's a synchronizing load, and it has it's also a fence. And then what we do is that we call SC, and in SC what we do is we store 1 in R2 and we try to store 1 in the lock address. So here is what we are actually trying to do. So the connotation of lock address is slightly different over here. So if 8R0 is not written to since the last load linked, right? So here it doesn't really matter what is the value of the lock address. What we really care about is that when we do store conditional, since the last time that we did a load linked, have there been any writes to this address? If there have been no writes to this address, we set 8R0 is equal to R2, alright, and we set the status equal to 1, otherwise we set the status equal to 0, alright. So that is the broad idea over here, that what we do is that when we acquire a lock over here, we basically execute this instruction in pairs. First we do a load and then we do a store conditional, and let's say in between them, if no other thread has accessed the lock address, then the lock address is set to 1. I mean, you know, any address is set to 1, but it can be another value, it can be set to 0 also, it doesn't matter. But the most important thing is we set the status to 1, we set R3 to 1. And if let's say that there has been an intervening write, we set R3 to 0. So what this basically does is, on the timeline, it just indicates that between the LL and the SC, right, this is an LL, okay, and the SC, no other thread has written to the lock address. So this also can be used as a synchronizing operation, right? So this definitely can be used to achieve something similar to what compare and set does. So you will find details in the book. So now, given all of these different synchronizing operations, what else can we do with them? So what we can do is that we can write a set of lock-free algorithms that don't actually require locks. So what is the problem with locks? If the thread goes to sleep after acquiring the lock, all the other threads wait, right? If the thread, all the other threads wait, there's nothing that they can do. In this case, however, you take a look at this piece of code. I'm trying to update the account balance and I'm not using any locks. Instead, what I'm using is I'm using these atomic operations, and all of these atomic operations, all of them can be implemented with basic changes to the coherence protocol, which let's say, let's consider the last example. We load this address in the M state, and then we simply wait till the subsequent store. And in the middle, if anybody else has invalidated it, then we say that this address has been returned to. Otherwise, we say it has not been returned to. That is all that we need to bother about. Okay. Now coming to this, I'll use the compare and set primitive to implement this. So first is that we have an an infinite loop. In the infinite loop, first we read the account balance, which was the same earlier also. Then we set T2 is equal to T1 plus 100. And then what we do is we do a compare and set. So in the compare and set, essentially what we check is if the account balance is still equal to T1, okay. So the account balance is still equal to T1, then we set the account balance equal to T2. So you can run two threads simultaneously. So what will happen is that if both do the cache together, one of them will succeed and one of them will fail. Why is that? Well, the reason is that one of them will atomically change the account balance from 100 to 200, and when the other thread performs the cache, its account balance will not match what it read. So that one will fail. So in this case, what we are essentially doing is that we have replaced a code with a lock and an unlock, which had high overheads. Lock and unlock, as you saw, you need so many functions. And furthermore, you need so many calls for just getting the lock and then doing the job. So we have kind of folded all of that into this simple piece of code that does not require locks. All that we need to do is we need to repeatedly execute these cache instructions until we are successful. When will we not be successful? Well, when there are concurrent requests to update the account.balance variable, that is when we will not be successful. Otherwise, this also works similar to an LLSC, similar to a load linked and store conditional, something that we saw over here. So it's a similar philosophy. So we read the account balance once, we update it, and before writing we check whether the account balance is the same as the old value, something that we read. If it is equal, we update it. And this entire cache operation happens atomically, which is the magic of atomic instructions. So as you can see that the cache might fail for a few threads because some thread would have had a successful cache and it would have updated the account balance. So threads will continue to iterate until the compare and set operation is successful, but once it is, they will get out. So we still, if we let's say consider the best case, we don't have to execute all the extra instructions of the lock and unlock code. We directly execute this and we are done. Of course, it's possible for a thread to starve in the sense it never gets the lock. That is because the status of the cache operation for it never returns as successful. Then of course there is a problem, but in practice this actually doesn't happen. So very rarely it does happen in practice. So it's not really something that most people should worry about. And lock-free algorithms consequently are very popular. Now, but let's say that we still want to eliminate starvation, right? So we don't want to entertain the possibility that one thread continuously tries to update its account balance, but it's not able to do because some other thread is getting in and updating the account balance in parallel, right? The cache is failing. So if we want to totally eliminate starvation, we go for wait-free algorithms. So in this wait-free algorithms, what happens is that one request T first finds another request R that is waiting for a long time. So each one of them, so let's say a request in this case would be a request to update the account balance. Right? And so what happens is that we can have an array of requests where we store all the pending requests. So once a request T comes, it tries to find another request in this array that has been waiting for a long time. So then R is, let's say, close to starvation because it is somehow not able to execute all of its steps correctly. So in that case, T decides to help R. In the sense, it tries to do the job that R was trying to do. So T decides to help R by doing it. So then what will ultimately happen is that, let's say R becomes the oldest message in the queue. All other threads will ultimately try to help R. So they will, one of them will have to be successful because now all the threads are trying to do the same thing. And either R will finish its job or some thread will finish the job of R on its behalf. Regardless of who finishes the job, this strategy ensures that no request is left behind. And such algorithms where the request of one thread actually first reaches out and helps the requests of other threads is known as an altruistic algorithm, right? Where you do something for somebody else. This ensures that our system is overall wait free, which basically means that if I have a set of instructions, if I have a critical section where I want to update something, right? And so let's say, I'm trying to acquire a lock or something. And so it doesn't matter any kind of a concurrent algorithm. I'm trying to update a lock or implement a shared stack or queue or whatever. But essentially, I'm trying to do some parallel operation. So the lock-free algorithm does not give us guaranteed completion. As you can see, there is an infinite loop. But in comparison, the wait-free algorithm will actually give us guaranteed completion because ultimately all the requests will help R. So basically, there is no starvation in wait-free algorithm because one request does help another request. And along with no starvation, the other nice thing is that requests are guaranteed to complete in finite time, if not bounded time. So let us now, given that we have seen, we have a very, very basic idea of lock-free and wait-free algorithms, let us ask a question, are all atomic operations equally powerful? So what does this actually mean? What is power? So let us define the consensus problem. So the consensus problem is that each thread proposes a value. So let's say we have 10 threads in the system. So thread 1 proposes 3, thread 2 proposes 5, and thread 10 proposes 7, and so on. So then we run a parallel algorithm similar to the algorithms that I have shown, similar to this algorithm, right? So this is a parallel algorithm if you think about it. They're all trying to do a cache, right? So then in parallel we choose one among the proposed values and everybody agrees. So let us say that we choose 5. So that is one among the proposed values and everybody agrees. So why is the consensus problem important? Because it's a theoretical basis of most concurrent algorithms, including the algorithm, for example, for deciding that which thread should get a lock. So assume that we have a single lock for a critical section and 5 threads are interested in acquiring it. Ultimately, one thread will acquire it and it will go and execute the critical section. So this is an example of a consensus problem because ultimately all the threads are agreeing on one thread which is kind of chosen as the winner, that goes ahead and executes the critical section and it unlocks and it gets out. After that, one among the remaining threads will again kind of be chosen as the winner, in the sense it will get the lock, it will execute the critical section and get out. So the fact that we are choosing one winner and that winner is going to get the lock, and furthermore the winner is being agreed to by all the threads, this is an example of a consensus. So the consensus problem kind of forms the basis of most parallel and concurrent algorithms, particularly algorithms that implement these data structures, like this parallel lock or something like a parallel queue or a parallel stack or something like that, right? So so in this case, the consensus problem is important. What is the problem again? We have multiple threads, all the threads, each thread proposes a value. One among the proposed values is chosen and accepted by all. What is the consensus number? It is the maximum number of threads that can solve this problem using a weight-free algorithm, right? So the consensus number is actually for a certain type of operation. So the consensus number, let's say for atomic exchange, would be the maximum number of threads that can solve the consensus problem using a weight-free algorithm, which means that we are, let's say, guaranteed to attain consensus in a finite amount of time using only basic register read writes and the atomic exchange primitive. So this clearly gives us an idea of the power of an atomic operation, the power of a concurrent operation, in the sense that it can solve consensus for how many threads. So there is a proof, I'm not getting into it, but you can read Herlihy and Shavitz's book, that the atomic power of atomic exchange, test and set, fetch and add, fetch and increment, and so on, even atomic, I mean all of this entire family of instructions, right? Exchange, test and set, fetch and add, fetch and increment, and so on, their consensus number is 2. So beyond 2 threads, they will actually not be able to solve the consensus problem using the constraints that we have described, which is that it should be a weight-free algorithm, and we will only use atomic operations of this type. So this basically constrains the kind of parallel code that we can write, and also for, let's say, acquiring a lock without starvation, for example, which will also be a consensus problem, more than 2 threads they will actually not be able to manage. So that is why every architecture needs to implement either the compare and set primitive, compare and set atomic operation, or the LLSC, the load linked store conditional atomic operation. Both of these have a consensus number of infinity, which means that for an infinite number of threads, they can solve the consensus problem, right? Which is an agreement problem, they can solve it. So this are by all means the most powerful, right? So I should add the word most powerful. And most architectures would implement some form of these consensus primitives, some form of these atomic operations, but they would also implement either one of compare and set or LLSC, because it's very important that we have an infinite consensus number. All right. So we have discussed a lot of coherence. So we have spent 2 full lectures discussing coherence. So what we will now do is we'll kind of wrap up this discussion on memory models, orders, coherence, and so on. So we will, in the next lecture, we will discuss a little bit about memory models. We already know a lot. We'll kind of summarize our knowledge, and we'll discuss about data races, which is kind of the cap on the bottle, right? So this has all the results that we need to write practical programs on extremely relaxed memory model machines.